Welcome back to a new episode of Cleantech Conversations. Today's guest is a familiar face. I'm joined by Jonathan Gifford, renewable energy journalist, content creative, and public speaker. Jonathan is widely recognized for his influential work at the industry journal PV Magazine, but for almost 2 years now, he has also been leading Climate Copy, a marketing agency dedicated to developing communication strategies, content marketing, and bespoke events for clients across the energy transition space. Jonathan, welcome to the show.
Sebastian, thank you very much for having me back again. It's a great pleasure.
Indeed. Last time we spoke and you walked us through the transition from P-PERC to N-type, Top Gun, and heterojunction. I remember very well. Today the focus is perovskite and tandems. But before going into details, I just learned that you returned from Australia. What did you see in terms of perovskite and tandems in the R&D space in Australia?
Yeah, it's quite a lot of activity is the short answer. Australia is at the far end of the world, as we all know. It's a long way from anywhere, but it's had a really special place in the development of PV technology, in particular the University of New South Wales, the UNSW, Martin Green, Stuart Wenham, these kind of pioneers of the early crystalline silicon industry and technology. So there are these renowned labs. There are great, wonderful teaching facilities. I think it was the world's first photovoltaic engineering degree that students could go and work on. And we were very lucky at Climate Copy to be able to tour around the laboratories and see a lot of activities in perovskite solar cells at the UNSW. But it's not only the UNSW. There's an organization now called ACAP, the Australian Centre for Advanced Photovoltaics, that's led formerly by Martin, but now led by Renata Egan. And that kind of brings together a number of Australian universities and research institutes to kind of coordinate their work on future-focused photovoltaic programs, and that includes perovskite solar cells.
And you talk about these R&D institutes for sure, right? But there's a whole ecosystem right now evolving, what we understand correctly, even beyond the R&D facilities. Can you elaborate a little bit on this in Australia?
Yeah, I wouldn't... Australia's no great manufacturing country, right? So the economy is not really built on building things. But there is a lot of innovation, and there is some efforts to commercialize kind of future-focused solar technologies, including perovskites. There's a company, HaloCell. Now that's a kind of reinvention of Dysol, you might have known. They're an early organic PV developer. They're now continuing to work in the perovskite field. There's some other innovative companies in the production equipment space, BT Imaging, you'd be familiar with, which was a UNSW spin-off. And also Sunfire that's working, but they're more in the kind of metallization space. So they were trying to commercialize copper metallization for heterojunction cells. I understand they're going through a bit of a transition at the moment. But there is support for Australian technological development and even manufacturing now from the Australian government. They're interested in kind of fostering the solar photovoltaic supply chain in Australia, providing some kind of manufacturing grants. And the most recent development was Suntech founder Zhengrong Shi, who was one of Martin Green's PhD students before he then went on to found Suntech. His new venture, which is Sunman, it's not so new anymore. So they work in lightweight modules, some are flexible as well. And I think they've got about 500 megawatts of production capacity, or maybe 500 megawatts of production a year in these kind of flexible modules and lightweight modules. So Dr. Shear is setting up manufacturing in Australia, and it will become Australia's largest module production site, also in New South Wales. So that's an exciting development.
I mean, it makes sense if you have R&D to let's say, develop this and over the whole value chain. But we come to this later also when it comes to other parts of the world. So you recently attended different perovskite conferences all around the world. So how should you describe the level of momentum and also the seriousness of this technology you saw at these conferences?
Yeah, well, there's a huge amount of activity. And it's always a case of trying to weigh up, hype versus genuine progress, right? Always with photovoltaic technologies. And so there is a lot of debate within the PV community about whether this is a kind of hype bubble with this technology. But from being within the community or observing the community, like as I do as a journalist, it really is encouraging. There's a lot of work. There's a lot of collaboration, I would say. Mm-hmm. There's a lot of openness within the community. That's always the case to some extent within the scientific community. But I was really encouraged to see the companies themselves also being very transparent about results, not only when it comes to efficiency, but also durability, which is a kind of key factor when it comes to perovskite commercialization.
You framed it very nicely in a nice article I read recently where you talked about Perovskite Trinity, which meant efficiency, stability, and also scalability. So why do all of these three simultaneously need to be happened for this technology to survive, or let's say to engage in multiple gigawatts? Why is it important that all of three needs to happen in parallel?
Well, I need to first of all acknowledge where this wonderful concept came from. So, as a good journalist, I don't have too many original thoughts, but I can tell you about what the other smart people have been saying. So, Peter Passmans, who's from Eternal Sun, they're a characterization and testing equipment supplier based in the Netherlands, who we work with at Climate Copy. And Peter came up with this kind of Perovskite Trinity concept. So you have efficiency, of course, you have durability, and then you have the ability to commercialize or mass produce, right? So like scalability in production, I suppose, would be the way to sum it up. And why is this important, right? Well, you're in production equipment, you know PV production pretty well. Like if you have a high efficiency product that's highly durable, but you can't scale production, that's not going to work. Likewise, if it's scalable, really scalable process, but you just can't get the efficiency up there, right? So you really those three things. And what we've seen in perovskite, as I understand it, from having looked into it this year, and also speaking to Peter at Eternal Sun, who is really very much across the technology, efficiency, huge gains have been made. There's a lot of promise in terms of how you can scale the technology with equipment suppliers like Fonadina, working very hard at developing platforms that can be rolled out in production. It seems like durability, reliability, this is the key one, right? Because unless you have a stable device, it will never really be commercial.
Yeah, and on these conferences, I mean, stability a couple of years back was, you mentioned device is stable when you produce and the efficiency survived until you could measure it, right? But I think in the last couple of weeks and months and years, improvements are made also here. Can you elaborate a little bit on these three main topics again? Efficiency, stability, scalability. What are the, let's say, main strongest progresses in these areas? What you observed?
Yeah, well, as far as I know, the PV perovskites, like perovskite was identified as being a photovoltaic material or having photovoltaic qualities really in the 2000s. So it's very, very recently. But what we've seen in terms of efficiency is huge gains extremely quickly, which is so impressive. So when you're looking at, you know, the cell level, a tiny little thing, maybe the size of your thumbnail, we're talking about 30% efficiencies already. When you're looking at mini modules, people are talking about 27%, I think maybe even 28%. I saw a presentation from Cubic PV just a few weeks ago. And then when you're talking about big scale, full scale modules, you know, people are pushing, I don't know, 20, 22, 24%, moving in that direction. And really in a very short period of time, these are huge results.
Indeed. And you mentioned to bring this now to mass production, or let's say pilot production. What we understand is really going out of the lab and into the real manufacturing world. So can you elaborate? You mentioned some companies and maybe some meaningful results, or why it is important that you're not staying on the small efficiency scale. Why it is important that you need this efficiency records also on large scale. What is the driving force behind this?
Yeah, well, we need large scale modules, right? We've got a largely, one of the beautiful things about PV is its ease to deploy, and so you want to be in a form factor that people are familiar with. So whether that's depositing onto, kind of G12 wafers, whether that's depositing onto, a large sheet of glass. These proven materials, these proven platforms are standardized within the industry. So you have to be able to scale it up. You can't make these kind of bespoke niche little products. We saw it in the early days of thin film. Remember, people were, or thin film commercialization, people were depositing onto roll-to-roll metal and then cutting it into strips and then assembling them and all these kind of novel designs. But PV is really built on the commercial PV. The modern industry is built on platforms that can be scaled, that's relatively standardized. So it's more plug and play when it comes to installation.
Yeah, and efficiency, scalability, clear. You need this to compare with the fantastic TOPCon and even also back contact models these days. But then I understand it's come to a limit, and then Perovskite Tandem gives you the push to 27, 38, or even above 30%. So durability. Can you elaborate a little bit also here why it's so important that we have these tests in, let's say, accelerated accelerated aging testing and even also outdoor tests? For whom and why is it for the community so important to look at this durability?
Yeah, well, we're still talking about PV project lifetimes of 20, 25 plus years. And, we're hearing in some markets that people are developing projects and IPPs are looking to own an asset for 30 plus years, right? That's becoming more commonplace. So unless you can trust the technology to perform over that period of time, your financial model is not going to work. No bank will ever lend you the money. And so you need to have trustworthy, reliable data that your module is going to stand the test of time. We saw failures, remember back in the day of the high feed-in tariffs, you could kind of whack anything out there in terms of technology and the returns were so good. But particularly these days, the margins are pretty tight right across the whole supply chain, including when it comes to selling the electricity as well. So you have to be able to trust that data. And like you said, I think you said crucially accelerated aging testing, because we don't have 20 years to test a perovskite module, right? So you need to find ways to accelerate that. I saw a great presentation from Cubic PV. In fact, they've developed a little kind of oven device that they can put their mini modules in and then test them in a really sophisticated way, but at an increased temperature, because they know that temperature accelerates degradation of perovskite devices. So that's a way to kind of speed up this testing process and provide that validation that you were talking about.
Absolutely, and you talked about this bankability and durability it's a key, especially when you talk about perovskite. But it was also in the past, and it's still also when you introduce new devices back in the days from Perk to TOPCon, but also TOPCon to back contact. And if you maybe just change materials, you need to show that it's bankable over 20, 25, 30 years. So you framed it in a very structured way in your recent article. You called it DNV level. So can you elaborate a little bit on this, and why is this framework so important for the industry?
Yeah, so when assessing new technologies, there are some methodologies that have been developed, and DNV GL, it used to be, I think, they've now DNV, they've developed a framework, a kind of commercialization framework where you can assess where a technology is on its commercialization path pathway. So they've got kind of 9 stages of that, 9 being ready to go. Let's get this out. The bank will lend to you. The insurer will back you up. You can develop that project. And by their assessment, it was, and this was work also by Total Energies, so a big energy major. These guys know about what it takes to invest in an energy product, and their assessment was that single junction perovskite products are kind of level 6. So
perovskite on glass, right? So just the device, perovskite on glass, single junction.
Yeah, exactly. So that would be at level 6, which means that there is an understanding about where the defects lie in the device, but they're not fully addressed. And then in tandem applications, they assess that Perovskite Tandem, so that's perovskite on a crystalline silicon.
Directly on it, so it's 2-terminal, right?
Exactly, so on a 2-terminal
just on device. A stack?
Yeah, okay. Exactly. Not 4-terminal, which is kind of a bit of a shortcut, but we can go into that later. Yeah. That's at level 5. So that's some defects are not fully understood, or some potential failure points are not fully understood. Some are, and some are addressed, but many are not. So there's still some way, according to that assessment, for perovskite commercialization to be achieved.
So when you talk about 5 and 6, so are there already kind of niche products, what we know from the past when it was PERC, but also TopCon? It was not that everybody did this at the first moment. There were always kind of emerging markets, niche markets, which took over. Do you see this already, or do we have to wait another level 7 or 8 until you get a first niche product for this?
Yeah, and well, in fact, the perovskite developers are already talking about it and are quite open about it. There are opportunities to deploy these devices. So one of them is indoor applications, which inherently doesn't sound like a great place for PV, but we've seen PV developers, OPV, organic PV developers in the past, try and address this niche. But I think what's different today than in the past with the OPV guys is that there's these Internet of Things devices, right? So we're putting these devices, fire alarms, sensors in our homes, the temperature sensors, the devices that kind of deliver the smart home. They need to be powered, and a nice way to not having to replace the batteries all the time is by having a kind of a mini module, tiny solar module in there, and perovskite developers can address that. And one of the beautiful things being that the module then isn't exposed to the temperature variations. It's not exposed to the full-on UV or moisture ingress through rain and hail and all sorts of things. So it's a much more controlled environment, so there's much less of a durability problem. The other application that I'm hearing more about and really only learning about at this stage is space applications, right? So solar started in space before it came down to Earth when it became viable for terrestrial applications. And it's still deployed in satellites, every single satellite. And generally they were these 3-5 devices, gallium arsenide, I believe. It's really high performance PV products. But the perovskite developers are looking very closely at this market. And from what I hear, getting a really good response from the space industry. And the space industry itself is growing very fast. So this is a growing opportunity. And also what I've heard is that the spectral match up in space, so the irradiation from the sun outside of Earth's atmosphere, it's the N0 spectrum, is very well, or perovskites are very well suited to that. So that's encouraging also.
Interesting. So PV everywhere.
Yeah, exactly. In the home and in the satellite. Yeah.
In the satellite, yeah. But on the satellite, I guess we are not about talking about gigawatt projects, whereas in the large projects where the developers are, they talking about gigawatt, right? And there you need this higher, let's say, DNV level where you need there. So how do you describe the current trust gap between these, let's say, developers and the work on the perovskite? So what do they need? What kind of transparency? What kind of collaboration is there missing that perovskite will really take off?
That's a big question. my intuition, and again, I'm not an expert, I'm just a journalist, but my intuition is that the gap is still very wide. There's still a long way to go. I've heard some industry experts talk about kind of 3 to 5 years of perovskite development. But your question was, what is needed? It will be data, and actually at UNSW, Martin Green took us up onto the roof of the UNSW building, where they've long had a testing array up there, and that array is now covered with perovskite modules, right? Full size modules. So the UNSW is partnering with the Chinese industry in particular, but they want to source perovskite modules from all over the world, and put these full-size modules up on the roof. There's another site in Manly, so they'll have some ground-mounted modules there, and just develop this real-world data. Actually, in Berlin as well, the HZB has done a lot of outdoor testing in partnership with, I think it's the University of Ljubljana as well, and getting some really good results in terms of how these products perform in the real world. Because at the end of the day, you can do all the laboratory testing you want. It's the real world that matters.
I agree. So let's talk about the manufacturing itself and also the ecosystem around. What signs do you see in the industry that it's getting a real supply chain, right? So we talk about new materials, right? You have to have new materials compared to the today's standard Top Gun or IBC, and also talk about equipment. So can you elaborate? Do you see signs that this will become more and more a real industry?
Yeah, it's really encouraging. I have to say, I was struck by not only, I mentioned before, the level of activity, not only the way people are collaborating and working together and sharing results, but also the kind of diversity of players getting involved. As you said, material suppliers. So I could see that there's a lot of ink suppliers who are really fine tuning their formulations in an attempt to deliver durability, to use fewer, potentially toxic materials. It would be ideal if we can move away from really heavy lead-based structures, but really trying to address stability and also materials that can be scaled, that can be rolled out in large-scale production. And from equipment suppliers, there were reports that there's some equipment suppliers are offering a turnkey line, which sounds a little premature to me, but it is really great that people are moving in that direction. And then individual process steps as well. So a number of deposition steps in particular. Also some people moving into roll-to-roll concepts as well. So there is a lot of both equipment and material innovation that's underway in preparation for companies looking to scale production.
And can you elaborate a little bit on where these companies are all coming from? Are they all from mainland China, or is it kind of a transition from different parts of the world?
Yeah, it's a good question actually, because it is striking that how international it is. So I mentioned cubic PV. There is an ecosystem in the US, laboratories, equipment suppliers, material developers, and the manufacturers, also in Europe. Particularly research institutes. Some of the research institutes are achieving really impressive results, and also material suppliers, and also equipment suppliers. And then, of course, Asia, right? China. Some of the Chinese manufacturers, Microquanta is perhaps the best known. And they're really demonstrating modules. They're now offering warranties on the modules that they're producing. So a 12-year product warranty, a 12-year product, 25-year manufacturer warranty, which is pretty remarkable if you think about it. And of course, their equipment partners are also looking to commercialize the equipment that they've developed in partnership with Microquanta.
Yeah, interesting. We are part of this transition as an equipment manufacturer, and we see it also on the global stage, and very encouraging results on the different parts. But let's focus a little bit on let's say, comparison in the past, right? We talked in the past about TOPCon heterostructures and the transition from PERC to TOPCon. So how does the current, let's say, tandem roadmap compare compared to the past, right? In the past, it was from BSF, big transition to PERC, from PERC, big transition to TOPCon, a little bit heterostructure. What do you see here? Is there similarities with tandem, or is there some differences?
Yeah, I think you very correctly observed earlier that crystalline silicon technology is approaching its kind of theoretical limits. Some of these back contact efficiency results are right up there. There's not much further than you can go with the device efficiency. So that answers the question, why perovskites, right? That's the reason. That if you hit the crystalline silicon efficiency limit, you need somewhere else to go. And that's why I think there's so much activity in perovskites at the moment.
Every year, the 0.5% efficiency increase. At a certain time with PERC, there was limits and you have to change to TOPCon. And now, as you mentioned, there will be a limit. So there are people who are saying, maybe we stay forever with silicon, TOPCon or IBC. And others say, no, the pressure is so high, we need to find another, let's say, materials. Maybe it's not perovskite, maybe it's another material, but you need to go to this. So what do you think in this transition? Will it be that it goes straight the line upwards, or you see more flattening and it stays with silicon on the global stage?
Yeah, it will depend on the technology itself. And so as you rightly observe, crystalline silicon technology, which is stable and proven and really just the workhorse of the industry, is also achieving just fantastic efficiency results, almost reaching the physical limits or the theoretical limits of conversion efficiency. So there kind of logically has to be a next step. And perovskite is very much looking like that next step. And when combined with a crystalline silicon substrate, can achieve some great results. So Oxford PV, which has production not too far away in Brandenburg an der Havel, their roadmap is to get to 30% tandem efficiency by 2030.
By 2030.
Yeah. So this would be a really huge achievement. And they're not talking about thumbnail-sized tandem devices. These are full cells.
And modules, right? So they have even modules which they're selling today.
Exactly, and this is a module efficiency that they're targeting. So this is a really promising outlook, and it will all be based on whether that Trinity can be achieved if they can prove the reliability of these high performance tandem devices.
I mean, that's basically answering probably already my last question. What would need to happen in the, let's say, when we meet again in 3 years, what would need to happen to call tandem PV a real commercial, let's say, product?
Yeah,
it's a Trinity, right? So
exactly, and I think it all hinges on reliability. So some in the community, in the PV scientific community, believe that we'll never get there with perovskites. I've heard the argument before that the rapid progress is perhaps due to an inherent flaw in the device. So it's so tunable. We've been able to achieve so much in terms of efficiency, but that might mean we can never achieve stability. I think we're getting a lot of understanding about what stability means for perovskite devices. So you have this meta stability, right? When you're trying to characterize perovskite devices, and there is a lot of understanding within the characterization, the testing community, about how we can accurately measure perovskite devices, because there are meta stability and different types of testing strategies need to be deployed. But yeah, I think at the end of the day, this kind of outdoor data, and then people who are willing to actually deploy projects in the field and then develop a track record will be the key.
Wonderful. So from my personal experience, I know that people thought in the past PERC will stay forever. Efficiency is right the way. You have very low cost of electricity. But at a certain time, Topcon took over, and everybody was surprised with this complicated or very defined processes. But people, R&D engineers, found a way to circumvent this. For sure, now it's a kind of more revolutionary way, but I personally think there will be a way to the tandem device. Anyway, Jonathan, thanks so much for your time and your thoughts today. So really enjoyed this discussion at Cleantech Conversations.
No, it's my pleasure. Thank you very much, Sebastian. And I have to note, when we were at the UNSW with Martin Green, he mentioned the interview you did with him, I think at Intersolar this year, as one of his favorite interviews that he's ever done. So I encourage all our viewers to check that out on the Cleantech.
Very good. And greetings to Martin. I really enjoyed this as well. One of the highlights this year.
Fantastic.
Thanks for stopping by.
Pleasure.